Let's look at the next example here. So for the circuit shown here, again we've got a three-branch parallel circuit. We've already got the reactances calculated for us, and we're given a source of 5 volts. So they want us to find in each branch the current and the total current, and then draw the diagram of the relationship. So this one we start off very simply with our Ohm's law relationship. Use Ohm's law to find each branch current in phasor form. So this is pretty simple. You've got your source, you've got your resistance, you've got X sub C, you've got X sub L. So it's just a matter then of running these values through your calculator. 2.2 into 5 volts, zero angle in this case. So we have 2.27 at an angle of 0, and our units of milliamps. The current through the capacitor then, V sub S over X sub C. So 5 to 5 into 5 gives us 1, and we move the angle of 90 degrees into the numerator, change the sign, we have 1 at an angle of 90 degrees in milliamps. And then finally, the current for the inductor, V sub S divided by X sub L. 10 into 5 gives us a 1/2. And then again, we do the same thing, move the angle out of the denominator into the numerator, change the sign. So we have 1/2 milliamp at an angle of minus 90 degrees. So the total current is the phasor sum of the branch currents. In this case, we just use Kirchhoff's law. So we're pulling all of the relationships out of our bag of tricks. So in this case, 2.27, 1, and 1/2 for each of the currents gives us 2.27 milliamps. J, when we do our conversion here, J 1 milliamp minus J 1/2 milliamp gives us 2.27 milliamps plus J 1/2 milliamp. Again, we have to maintain our phasor form here and our vector sum in rectangular format. So the next step then, we convert our rectangular form into our polar form. So we have the I squared plus I sub C minus I sub L squared, and the inverse tangent gives us then an angle, a current total of 2.32 at an angle of 12.4 milliamps. So I hope you're getting used to doing these conversions, turning them into polar form, because in most cases when dealing with multiplication and division, it's easier to use the polar form. The current then is 2.32 milliamps, leading the source by 12.4 degrees. So if we look at our relationship here, the diagram, you can see we have again our current through the conductor, or through the capacitor and the inductor, and then we have I total, I through the current through the resistor, and our source laying on top of that. So in this section, we'll take a look at the resonant condition in an ideal parallel LC circuit, assuming no winding resistors. Sometimes we make that assumption, and the problem will state that, so it makes the calculation easier. Then we'll examine the more realistic case where the resistance of the coil is taken into account. So the condition for ideally parallel resonance occurs when X sub C equals X sub L. So we've seen that. The frequency at which the resonance occurs is called the resonant frequency, just as in the series case. When X sub C equals X sub L, the two branch currents I sub C and I sub L are equal in magnitude, and of course they're always 180 degrees out of phase, and you can see that in the phasor diagram. Thus, the two currents cancel and the total current is 0. Since the total current is 0, the impedance of the parallel LC circuit is infinitely large, the ideal resonant conditions then are stated. X sub L equal X sub C. The impedance goes to infinity. Okay, so we can see in our relationship here, our schematic diagram, the inductor, the capacitor, and then our resonant frequency would be calculated using the relationship as we've learned. And again, we see the current waveforms and the phase relationships. For an ideal, in this case, no resistance, parallel resonant circuit, the frequency at which resonance occurs is determined by the same formula, just as we've learned it. Okay, so 1 over 2 pi, the square root of LC. A tank circuit then is a parallel resonant LC circuit. The term tank refers to the fact that the parallel resonant circuit stores energy in a magnetic field of the coil and in the electric field of the capacitor. The stored energy is transferred then back and forth between the capacitor and the inductor on alternate half cycles as the current goes first one way and then the other. When the inductor de-energizes, the fields collapse, the current reverses. Again, refer to Lenz's law. And the capacitor charges and vice versa. The concept is then illustrated in these two schematic diagrams. So we can see the waveform here, what's happening with the impedance in a resistor at resonant frequency and the relationships above and below resonant frequency for the reactances. The generalized impedance curve then for a parallel resonant circuit shows that the circuit is inductive below the resonant frequency, resistive at resonant frequency, and more capacitive at resonant frequency. So this is probably a good graph for you to copy down in your notebook and refer to so that you have an idea of what's going on when we do these types of resonant frequency problems. Current and phase angle at resonance. In the ideal tank circuit, the total current from the source at resonance is 0 because the impedance, as we said before, is infinite. In the non-ideal case, when the winding resistance is considered, so we bring in whatever resistance is there in the winding, there is some total current at the resonant frequency, and it's determined by the impedance at the resistance. So if the relationship says here the total current is equal to the source, then and the impedance, that little r, is telling you at resonance. The phase angle of a parallel resonant circuit is 0 degrees because the impedance is purely resistive at resonant frequency. So looking at bringing in the effects then of a winding resistance on a parallel resonant frequency, when the winding resistance is considered, the resonant condition is expressed then as 2 pi, the resonant frequency L, and something called the quality factor, the Q. Q squared plus 1 divided by Q squared, which gives us 1 over 2 pi FR by the capacitor. So we're just establishing a relationship between the two. In this case, the Q is the quality factor of the coil, X sub L, and R, the resistance of the windings. Solving for the resonant frequency then in terms of the quality factor yields then that relationship. All we've done is moved our terms around, and now you can see here we have our familiar square root of LC, and now we have the square root of Q squared plus 1. So all we've done is manipulated this first equation and solved for the resonant frequency. When the quality factor is much greater than 10 or equal to, the term with the Q factors is approximately 1. So they're giving you a rule of thumb here that this relationship is telling you then if we have a relationship such that the Q is greater than 10, so we have 10 squared plus 1 gives us 101, and a factor then of 0.995 or equivalent to almost equal to 1. Therefore, the parallel resonant frequency is approximately the same as the series resonant frequency as long as Q is equal to or greater than 10. A precise expression then for the resonant frequency in terms of the circuit component values then is, and you can see we've stuffed everything into this relationship. We've got the winding resistance squared, we've got the capacitance, we've got the inductance, and we've got the familiar term in the denominator. This precise formula is seldom necessary, and the simpler equation of resonant frequency 1 over 2 pi times the square root of LC is sufficient for most practical situations. Okay, you'll only dive into this one if if there is a deep dive and you want to understand what's going on with the minuscule winding resistance. So I'm going to let you go ahead and solve this. Find the precise frequency and the value of Q at the resonant circuit. So we've got your values given here with a winding resistance. Go back to these relationships and solve for the frequency and the Q of the circuit. Okay, this is the example as solved in the textbook. You can see everything was taken into consideration to solve it. Pull out your calculator. This is a good one for calculator fundamentals, and make sure you get the same relationship, 2.32 kilohertz in this case. In this case, we calculate for the quality factor. We find X sub L, so we find the reactance in this inductor, this 1/10 Henry inductor, and we get a reactive component of 1.46 k ohms and a Q of 14.6. Note that since the quality factor is greater than 10, the approximate formula then can be used. Okay, so we didn't need the resistance of the winding. So when we come back, we hit the next section here where we combine series and parallel together in our circuit analysis.